All right, welcome back to another week of statistics. We are talking about 6.3. This is the Poisson distribution. It's not the Poisson distribution, it's the Poisson distribution. And for the most part, this distribution is used primarily for time intervals. There are other uses for it, but for the most part, it's generally used for time intervals. So what I mean by that, let's take a look at example one. So a McDonald's manager knows from prior experience that cars arrive at the drive-thru at an average rate of 2 cars per minute between the hours of 12 noon and 1 p.m. The random variable x is the number of cars that arrive between 12:20 and 12:40. And so that would follow a Poisson distribution. The idea here is that there's an average rate per measure. Could be minutes, could be hours, could be days, whatever that may be. But there's an average rate. And then we basically ask, okay, well then what's the probability of a certain amount of things happening between a certain interval of time? Okay, and that's what I mean by it's primarily used for time intervals. So what we're going to be talking about here, we're not going to do everything the book talks about here, but there's a couple of symbols that I do kind of want to explain because the book uses it a lot. We're not going to be using this formula, we're going to be using the calculator. But I do want to talk about what these symbols mean. So the first symbol that I want to talk about is, is this symbol, which is lambda. And that's how I draw it. I don't know, it's not as good as some people. So lambda is the given rate, right? So in that example, the given rate was the 2 cars per minute, okay? And then the t is the time interval. The time interval that we're looking at, okay? So this is the one that we're looking at. So, for example, because we wanted to know between, in that example, we wanted to know between 12:20 and 12:40, then t would have been 20 minutes, okay? Now, both of these have to be measured in the same unit. So, for example, if the given rate is, let's say, cars per minute, then the time interval has to be minutes. If it were cars per hour, then the time interval would have to be in hours. So we might have to convert, right? There might have to be some conversion. But the idea is that they both have to be the same. So, okay, good. So now let's do something real quick here. Here we go. All right. So the Poisson distribution, let's just go ahead and bring up the calculator. And I'll bring it up so that you guys can see it too. There it is. Okay, so Poisson distribution. If we go to our second vars, so to the distributions, here's all of our distributions that we've been using before. Again, I'm going to go up because it's at the very bottom, or it's close to the very bottom. And here's Poisson PDF and Poisson CDF. So again, let's go over what these mean. So Poisson PDF would be the probability of exactly X occurrences. Let me fix that. Occurrences in a given interval. Okay, so it's the probability of exactly X occurrences in a given interval. So for example, if we looked back at that example the book used, 2 cars per minute arriving at the drive-through, and let's say we wanted to know, okay, well, what's the probability that exactly 15 cars arrive in this 20-minute interval? Sure, we would just use Poisson PDF, okay? Poisson CDF, what do you guys think that's going to stand for? This is going to kind of follow a theme with all the different distributions. This is going to be the probability of at most X occurrences. So once again, this is for X for being less than or equal to X, okay? So the probability of at most X occurrences in a given interval. Okay, and so those are the two things we're going to be using in this section, Poisson PDF and Poisson CDF. So let's take a look at this example here. Can we get, okay. And so same situation, 2 cars per minute between 12 noon and 1 p.m. So determine and interpret the probability of the following events. Exactly 6 cars arrive between 12 noon and 12:05. So we want to calculate that probability. So what we're going to do here is let's work on this example. So we're talking about this example here, and this is example 2 in the book, and we're on part A. So exactly 6 cars arrive between 12 noon and 12:05 p.m. So because it's saying exactly 6, well, let me not get ahead of myself. Lambda, what's the rate? The rate is 2 cars per minute. Okay. T, what's the interval we're talking about? In part A, we're talking about from 12 noon to 12:05, so that's 5 minutes, right? And then for the calculator, we are going to need X, which is 6, okay? Now, I kind of got a little ahead of myself here. There's one more thing we have to talk about, and that's going to be the average. So it might be pretty straightforward, but we gotta clarify this. So the average, mu, is always going to be equal to the rate times the time interval, right? If I tell you that on average 2 cars arrive every minute, and I'm asking you how many cars are going to arrive in 5 minutes, what would you do? That's just a simple multiplication problem, right? You would take that 2 and you'd multiply it by 5. Or in general, you're going to take lambda and multiply it by t. Okay, so we're going to need this for the calculator. So mu is equal to, in this case, 10. All right, and now what we can do is we can go to our calculator, and there it is. We can go to Poisson CDF. Let me restart here. So we go to second vars, to our distribution. We choose Poisson PDF because the question says exactly 6 cars. And so we're going to enter there. Here's our mu. So our mu is 10. So our mu comes from those two different things, the rate and the time interval multiplied together. And then the x value is going to be 6. And we're just going to hit that, and we get a probability of about 6.3%. And so the answer to this, and we used, remember we want to show what we used, so we used PDF like this. We plugged, we already showed all that stuff there, but anyways, and we got something that looks like that, and so we get 6.3% as our answer to part A. So let's take a look at part B. Example for part B. Fewer than 6 cars between 12 and 12:05. So for this one, the rate is the same. The time interval is the same. The x value is the same. The mu is the same. 2 times 5 is still 10. However, because we want to know the probability of fewer than less, or less than or equal to 6 cars, or fewer than, we're going to use the CDF. So we're going to use Poisson CDF. And what we're going to do is plug all that in. So Poisson CDF, mu is 10, x value is 6, and there's our probability. So about 13%. So it turned out to be something like this, and so we get about 13% probability. Okay? And part C, and this is a good one to go over because I don't think I went over this very well in the last few sections. So let's talk about this a little bit more in depth. Part C, at least 6 cars between 12 and 12:05. Okay. All of this stuff is currently the same in this example. Okay. However, now, if we think about a distribution, and it doesn't matter what the distribution is, this is always the same. So I'm just going to draw, oof, that looked really bad. Okay. Draw some sort of distribution, wasn't much better. And if I'm picking some sort of x value, right, let's say I'm picking an x value here. When I do CDF, it's giving me all this stuff that's less than or equal to it. Okay? This is CDF. Right? It's giving me all the probability all the way up to x. So if I need to know the other side of this, well, that's the other probability, the other percent. So for example, if this, let's say, turned out to be 0.8 or 80%, then what would this side have to be? Because it's a probability distribution and it has to add up to 1, this would have to be 0.2 or 20%. Right? So it's the 1 minus the CDF to get the other side. Okay? And so that's what part C is talking about. So for part C, we're going to do the CDF, which is what we already did in part B, right? Because we didn't change any of these values. So we know from part B that less than 6 cars is a probability of 13%. And so what's the probability of 6 or more? Well, that's the other percent. And so 100 minus 13%, or 1 minus 0.13, would give us what percent? And that would probably give us 87%. And so we would have 87% for part C. Okay? So, apologize if I didn't explain that as well on the last sections, okay? But that goes for all distributions, okay? So the next part of the book talks about the mean and standard deviation. We already talked about the mean because we needed it for the calculator. And the mean is just lambda times t, right? It's the rate. Oh, let me get that out of the way. Lambda times t. And the standard deviation just happens to be the square root of the average. So it's actually pretty simple to do those things. So we have the average of a Poisson distribution is lambda t, right? Rate times interval. Rate times interval. And the standard deviation of Poisson distribution is the square root of the average of lambda times t. Okay? Let's take a look at some examples. Let me actually do a couple problems. Just make sure we're all on the same page here. So here is, again, at the end here, we get the calculator instructions in the book. So you can review those as well. I'm going to go ahead and go into section 6.3 and let's do a couple of examples here. So we're going to do some examples. How about number 8? Looks good. Which you can't see yet. Whoops. Okay, number 8. So in problem 7 and 8, the random variable x follows a Poisson process with the given mean. Okay, so assuming mu equals 7, compute the following. Okay, so number 8. How are we going to find the probability of 10? If mu, let me write this, if mu equals 10 for the whole, not 10, 7. Sorry. If mu equals 7 for the whole problem, number 8, what's the probability of 10, of exactly 10? So, because it's just one number, that's PDF. So we're going to do Poisson PDF, and our mu is 7, and our x is 10. Okay, and let's bring the calculator back up, and we are going to do Poisson PDF, mu 7, x 10, and about 7.1%. For part A. For part B says, you guys can still see this, right? Yep. Part B says x being less than 10. So, what are we going to do here? Well, we're going to do CDF. So Poisson CDF, average 7, x is 10, and we get 90.1%. Let me go ahead and show us what we were doing here. That was CDF. And we got 90.1%. All right. And so on, right? So part C, where are we here? So part C, there we go. Probability that x greater than or equal to 10. Well, That's going to be 1 minus the CDF, the one that we just did, right? So 1 minus Poisson CDF of 710. And so what's the other percent there? Looks like 9.9%. Right? Fill that out, make it 100. And now part D, which is really the one I wanted to go over because that's not the example we've done yet. So part D, how about the probability of being between 7 and 9? So just to put some context here, if we were talking about 2 cars on average per minute, and let's say maybe we're looking at a 3.5 minute interval, what's the probability that between 7 and 9 cars arrive? Okay, that's what this question would be getting at. So how are we going to answer this question? Well, if we think about this visually, if I have a distribution, and let's say I have 7 here and I have 9 here, right? I essentially want to know what this area is, what this probability is, okay? And I have PDF that can give me exactly one value. That's not going to be helpful. And I have CDF, which can give me less than a certain value. That's going to be helpful. So what we're going to do is, if I get the CDF for 9, right? The CDF for 9 gives me from 9 all the way left. And if I get the CDF for 7, there's the CDF for 7. The CDF for 7 gives me all of this. And hopefully we can see that what we want would be CDF 9 minus CDF 7, right? Because we take all this area and we subtract this area over here. Okay? So, there, now you can see it. So, let's do, we have our CDF for 7, I just noticed. So now let's do our CDF for 9. Actually, we don't have our CDF for 7, sorry. I was looking at it the wrong way. Okay, here's our CDF for 9. So our Poisson CDF for 9 is about 83%. Sorry, that's not the answer. 83%. Poisson CDF for 7 well, we're going to go figure that out right now. And that's about 59.9%. Okay, now we do this idea where we're just going to subtract the two. So I'm going to grab that, and I'm going to subtract that. And that gives me about 23.2%. So depending on when we rounded, we might get a different answer, but hopefully something very, very close to 23.2%. Okay? There's our answer for part D. So that's how we would find probability of between two certain values. And that is going to be it for the Poisson distribution. A couple more homework problems, and I will see you on the next one.